Okay, so happy to welcome our next speaker, Neerav Atre. He's a fourth-year PhD student at CMU. His interests are in networking and performance modeling, such as building high-performance network systems and proving theoretical properties about their stability and performance. Please take it away.
Thank you, Ramesh. Morning, everyone. It's my pleasure to be here, and I'm really excited to present this work on mitigating temporal algorithmic complexity attacks on network functions. This is joint work with my wonderful advisor, Professor Justine Shetty, and my collaborators at CMU. So our story today starts with network functions. As you all probably know, NFs are key components of the modern internet infrastructure, and they serve a number of important purposes. For example, NFs are used to implement firewalls, load balancers, WAN optimizers, intrusion prevention systems, etc. However, as a result of this ubiquity, NFs are also prime targets for denial-of-service attacks. Recall that the goal of a DOS attack is to consume as much of a target system's resources as possible, thereby inhibiting its ability to serve legitimate users. Now, DOS attacks come in a variety of flavors or classes. Earlier today, we heard about DDoS attacks, which are a type of volumetric attack. There's also amplification attacks, for example, DNS amplification. Today, I'm going to tell you about a class of DOS attacks which can be significantly more potent than these other classes. And these are algorithmic complexity attacks, or ACAs. So the setup is as follows. We have a network function, which is serving a number of innocent users. And in order to process their traffic, the NF is going to be running some underlying algorithm. Now, the NF is likely designed for the common case. So the traffic from these innocent users is probably going to just stream through this algorithm without too much of a holdup. This is the common case. Now, imagine if you had an attacker whose goal is to attack this NF in order to produce denial of service. The way that the attacker is going to orchestrate this is by crafting and sending input corresponding to the worst-case behavior of this algorithm. So instead of the nice streaming traffic that we see on the right, we might see the attacker's traffic experience a path that looks something more like this. As you can tell, the attacker is able to use a lot less bandwidth, but still consume a large fraction of the NF service capacity, thereby causing the innocent traffic to be dropped, producing denial of service. It turns out that several NFs on the internet are inherently vulnerable to these kinds of vulnerabilities. So, for example, TCP reassembly, regular expression-based deep packet inspection, packet classification, etc. Now, I want to give you a concrete example of where we see this in practice. Pegasus is an FPGA-based intrusion detection system that we built at CMU and appeared at OSDI 2 years ago. Now, Pegasus is really fast. It's capable of processing 100 Gbps of traffic in the common case, all within the footprint of a single server. The problem is that some of the design decisions we made for Pegasus introduced two ACA vulnerabilities in the Pegasus data path. The first one appears in the TCP reassembler, which is responsible for reassembling TCP flows from out-of-order packets. The second is the CPU-based full matcher, which performs regular expression search on certain traffic. And this is vulnerable to classic RDoS-style attacks. Now, a key point I want to highlight here is that ACA vulnerabilities are not bugs. They might be artifacts of perfectly reasonable design choices that a system architect might make. So the question is, if they're not bugs, how do we fix them? That's exactly what we're going to look at in this talk. So first, we're going to look at how to model ACAs on network functions. Next, we're going to try to answer this big question of how does one defend against them. And finally, we're going to look at a brief evaluation in the context of the Pegasus IDS. So first, let's take a look at how to model ACAs on NFs. At the heart of our abstraction is a network function which serves traffic as it appears on an ingress link, in this case rated at RGBPS. So the NF is designed to serve innocent traffic, which is depicted in purple here, And the volume of this traffic depicts the innocent the innocent bandwidth, which is r sub I Gbps. In response, the NF is going to produce some traffic on the output link, which corresponds to the good put. The way we model an attacker is by introducing some attack traffic on the input link. In this case, r sub A Gbps depicted in orange. And as a result of this, we're going to see a drop on the output link. So the attacker is going to be able to drop some output or drop some good put, which is representative of the damage that they're doing. So the way we model this, the way we quantify the impact of ACAs is by using this novel metric called the displacement factor, or alpha. So we define alpha as the ratio of the good put displaced by the adversary, so this gray region here, divided by the attacker's own bandwidth, which in this case is the orange region. Very intuitively, the DF captures the harm that the adversary is able to induce relative to the amount of effort that they exert. And the adversary's goal is to maximize this quantity alpha. OK, so now that we know how to model ACAs, let's take a look at how one might defend against them. So first, I want to tell you about two existing approaches that are state-of-the-art and commonly used in systems today. The first one is resource isolation. So the idea is very simple. We're going to give every user a fixed slice of the service time, as is common in operating systems and cluster compute frameworks. In the networking setting, this translates very naturally to fair queuing. The problem is that while fair queuing works in stochastic settings, it doesn't actually work in an adversarial setting. And we'll see exactly why in a few slides. The second approach, which is once again state-of-the-art, is to use application-specific patches. Put simply, we're going to patch the algorithm so that the worst case is not too bad. The problem is that using these patches involves trading off some system property or the other in exchange for ACA resilience. For example, the common case performance or the ability to serve certain kinds of traffic. So these patches severely limit what your system can do. So the question we ask in this work is there a general approach to ACA mitigation that does not limit the kind of traffic we can serve or throttle common case performance? Our key insight is that if we reorder packets in just the right way, we may be able to selectively deprioritize the attack traffic without actually knowing what it is. And the point is packet scheduling. So really what we're proposing here is to interpose a scheduler between the ingress link and the NF. And the scheduler is going to decide the order in which packets are going to be served. So the question is, what should this policy here be? Let's first take a look at two existing policies. So NFs typically use first come, first serve, or the de facto scheduling policy, or some fair queuing variants, such as weighted fair queuing or DRFQ, in order to ensure flow-level fairness. So how do these fare in an adversarial setting? Let's first take a look at FCFS. The policy is simple. We're going to serve packets in the order in which they appear on the ingress link. So here we have innocent users who are talking to an NF, and this is what the system state might typically look like. So on the x-axis, we have discrete time. The first row depicts NIC time, which is the packet bandwidth, and the bottom row depicts the CPU time, which is the amount of time it takes to serve this packet. So we see here that innocent packets are fairly large, but don't take a lot of time to be processed. So the system is underloaded. Now consider an attacker who wants to attack this policy. An attacker might realize that the optimal strategy against FCFS is to try to use minimum size packets, thereby maximizing their packet rate. And in conjunction, use maximum job sizes in order to maximize their work per packet. Overall, this induces the maximum amount of work in the system. So this is what the system state might look like when we mix in attack traffic. So we have these orange attack packets, which don't actually consume a lot of NIC bandwidth. However, they expand on the CPU side, causing innocent traffic to be displaced. We show in the paper that the displacement factor under FCFS is actually lower bounded by this ratio of Jmax to Pmin, which is the maximum job size to the minimum packet size. And as this quantity tends to infinity, so does the displacement factor under FCFS. So this is not great. Let's take a look at fair queuing. So the policy here is to partition the processor time equitably between the different flows. Unfortunately, I don't have time to walk through this example in detail, but the intuition is that by using a large number of flows, the attacker is able to trick the fair queuing scheduler into giving them more than their fair share. And so here we see that once again, using small-sized packets, the attacker is still able to achieve roughly 3/4 of the available service capacity. We show in the paper that the displacement factor under fair queuing is also lower bounded by the same quantity. And fair queuing also has an unbounded DF. OK, so if we go back to our question of how existing policies fare in an adversarial setting, the answer is not great. So if we intend to use scheduling, we really ought to do better than this. So what can we do? Well, there's two intuitions we should have. The first one is that it's the large jobs with size j max that are really killing our displacement factor. So why don't we try to prioritize small jobs instead? And second, the packet size is useful information that we're throwing away. So we should also try to incorporate this into our policy. So that brings us to this policy, which is packet size weighted shortest job first, or simply weighted SJF. And the policy is simple. We're going to prioritize packets with the smallest job size to packet size ratio. So how might this help? Well, imagine a system in steady state where we have a weighted SJF queue with these 3 innocent packets. And the packet sizes are P1, P2, and P3, but all of the job sizes are the same. So now consider an attacker who wants to displace one of these packets using some of their own. The way the attacker is going to do this is by inserting this packet with packet size P4 and unit job size. If the attacker's packet size was any smaller, it wouldn't be scheduled. And if the job size was any smaller, it would introduce slack in the system capacity for innocent traffic to be served. So we see here that the attacker has to put in P4 bits of work, or P4 bits of attack bandwidth, in order to displace P3 bits of innocent traffic. And it has to satisfy that relationship over there. So this is interesting. We observe that the attacker puts in more bits than they want to displace. So how does this help? Well, that brings us to the main result of this, the main theoretical result of this paper, where we show, using some math, that the displacement factor under weighted SJF is actually upper bounded by 1. So we find that weighted SJF not only has a bounded DF, but a constant one. If we put this into simple terms, weighted SJF guarantees that for every bit per second that the adversary wants to displace, they have to put in at least 1 bit per second of their own traffic into the attack. We actually show something slightly stronger in the paper. So we can show that the displacement factor under weighted SJF is actually upper bounded by the min of 1 in rho sub I, where rho sub I is the load on the NF due to innocent traffic. So for example, if the load of the NF was 10%, the attacker would have to put in 10 bits per second in order to displace 1 bit per second of attack traffic, significantly mitigating the potency of ACAs. So that brings us to our proposed framework, which we call SurgeProtector. SurgeProtector interposes a weighted SJF scheduler between the ingress link and the NF, which guarantees, in theory, an upper bound of 1 on the worst case DF that the adversary can achieve. In fact, we can show that this is actually independent of the load on the DF, the packet and job size distributions for innocent traffic, as well as the application itself. So this is a general purpose approach. So there are a few practical issues that crop up when we attempt to deploy SurgeProtector in practice, and I'm going to highlight a few of them here. So the first thing you might be wondering is, well, we don't know job sizes. In systems, the job size is rarely known ahead of time, so how do we schedule based on this information? As a standard in queuing literature, we rely on heuristics. So we effectively query the system for its best estimate of the packet service time and use that as a proxy for the true job size. Second, it turns out that keeping flows in order is sometimes important. For example, we know that TCP performance degrades significantly when we have out-of-order packet delivery. Weighted SJF doesn't guarantee in-order packet delivery, but we design an in-order variant of weighted SJF with similar properties. And finally, well, we've introduced a brand new attack surface for the adversary. So what if the adversary attacks the scheduler itself? To deal with this problem, we design a heap with guaranteed worst-case time complexity. So this is an augmentation of the hierarchical find first set queue, which allows both DQ min and DQ max operations simultaneously. This is implemented both in software, as well as we have an RTL implementation for an FPGA, which is fully pipelined. So finally, I'm going to talk about a brief evaluation in the context of Pegasus. You can read more about this in the paper, but I'm just going to touch on one application here. So here we're looking at Pegasus's TCP reassembler. On the x-axis, we're going to sweep the attack rate for the attack bandwidth. And on the y-axis, we're going to look at the good put for both FCFS and SurgeProtector augmented Pegasus versions of Pegasus. So we see that in the absence of any attack traffic, both versions of Pegasus are able to keep up with the input rate. Great. So we see 10 Gbps of good put when there's no attack. However, as we increase the attack rate, we find that FCFS has a significant cliff. So for example, with just 0.3 Gbps or 300 Mbps of attack traffic, the adversary is able to displace roughly 8.5 Gbps of innocent traffic. So overall, we see that in the context of both applications, SurgeProtector yields a 90 to 99% reduction in good put loss. So in conclusion, we saw that network functions are susceptible to this class of DOS attacks called algorithmic complexity attacks. And here in this work, we designed SurgeProtector, which is a general-purpose mitigation framework that uses novel insights from adversarial scheduling theory to provably upper bound the harm that an adversary can induce. These are my collaborators, and we have we've open sourced our code for both the adversarial queuing simulator as well as the software and hardware heap implementations, which you can find at the Git repo. Thank you, and I'm happy to take any questions.
Questions?
Hi, Neera. Very nice work. I was wondering how general your approach is. So can you handle all kinds of ACA attacks? Are there some ACA attacks you cannot handle?
That's a good question. So here, the main limitation I can think of is the job size estimator. So here, our approach, the theoretical approach, is able to handle all of these, all kinds of ACAs. But when you try to incorporate this into a practical system, you really need to worry about having a good heuristic. So in the paper, we demonstrate that you can actually do this very easily for the two applications we consider, so TCP assembly as well as regular expression search. Simple heuristics actually tend to be very powerful job size estimators. But this is only scratching the surface as far as designing heuristics goes, and we're looking forward to seeing the design of adversary-proof heuristics. And I also want to add to that point in terms of practicality. We can use, for example, things like preemption to handle inaccuracies in our job size estimation. So in terms of the applicability, it's applicable to all ACAs. But in terms of the implementation, there are things that need to be things that you need to do to kind of use it in your system.
Any other questions? I have a question, actually. If the adversary knows your heuristics for estimation, could that actually, be used against the system?
That's an excellent question. So we actually look at this in the paper, and so we basically evaluate the case where the adversary has perfect knowledge of the heuristic and how what the job size distribution looks like. So it turns out that because our heuristics work reasonably well for innocent traffic, the adversary is not able to subvert the heuristic to a significant degree.
Okay.
So here, for example, we see for different loads, the absolute difference in the heuristic, the absolute difference in the displacement factor when the adversary knows the heuristic versus when they do not. And so we see a roughly 0.05 change in the absolute difference, which is roughly a 5% compared to the theoretical bound. So it's not too bad.
Okay.
Thanks for the talk. So maybe I just missed, but could you tell me more about the job size estimation? So do service owner need to implement some logics to give some estimations?
Right. So yes. So the one thing you can use, we designed SurgeProtector to be a kind of a drop-in scheduler that you can put in front of your system to protect it from ACAs. The one functionality that you would need to add to your system is the ability to query the system for the job size estimate. And so the main point here is that you have to come up with a heuristic that that gives reasonable estimates for job sizes. So I want to give you a quick example of what this might look like. So for example, in the case of TCP reassembly, if you're implementing this using, for example, a linked list, where you're tracking out-of-order flow state using a linked list, you can estimate the job size as the size of the linked list. So this is kind of a very simple heuristic which works well in practice. For your application, you might design the heuristic either by hand, or you might use some mechanized tools like static analysis to come up with like paths, and you can map them back to the input. So the idea is, for a given input, you need to know the job size, and you need to kind of design the heuristic that does that. Does that answer your question?
There's one more question here.
Go ahead. OK.
Okay,
really nice talk. Yet another question about job size estimating, not trying to DOS out other questions. One way that you could have variable performance is because of the way the function's implemented. For example, a fast path, slow path kind of strategy. Have you thought about how, for a given class of functions, you might estimate job sizes with a system that is itself choosing, to vary the performance based on how it implements it?
I see. So if I understand your question correctly, like you might have a system which has a fast and slow path, and the system is going to try to process as much traffic as it can on the fast path, send whatever it can to the slow path. So if you do have this design, which actually Pegasus does, and so that is a good example, in that case, you would hopefully the fast path is fast enough that you don't actually have this kind of enough performance variability to cause ACAs. We would expect to see ACAs on the slow path because you have a lot of variability. And in that case, the split design is actually perfect because you can use your fast path to kind of pre-process the traffic in order to develop heuristics. So this is kind of what we do in the case of Pegasus, where we have a set of initial filters, and we use kind of the fast path to give a first look at the traffic in order to come up with an estimate for the slow path. So we think it would work actually perfectly for those kind of applications because you have a chance to look at the data before you schedule it. Does that make sense?
That's great.
OK. One last question.
Thanks for the great talk. I have a question. If the attacker changes their policy, like currently they are sending traffic that has large drop size, but what if in your system, what if they send traffic that has smallest drop size? Does it mean that the normal traffic will be deprioritized by the attacking traffic?
Good question. So when I was talking about the large jobs with small packet sizes, that is the optimal policy for first come first serve and fair queuing. It turns out that in the context of weighted SJF, which is the policy you use, it doesn't matter what the adversary does. So they have to. It turns out that the adversary actually has to solve an optimization problem in order to find the right parameters to use for their traffic. But even if they do that, the bound will always hold. So that is to say that when we say that the weighted SJF has a DF upper bound of 1, that is actually considering accounting for the fact that the adversary uses the optimal strategy in order to attack the ACA. So that bound will always hold.
OK, let's thank the speaker. Thank you very much.